GenAI and MLOps Part 28. This episode has 5 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. What is ML monitoring? Here's a strong way to approach it. ML monitoring is the process of continuously tracking and analyzing machine learning models, data, and infrastructure in production to ensure the system performs reliably and accurately over time. The goal of ML monitoring is to detect issues early and maintain model quality, business performance, and operational stability. Key areas of ML monitoring: 1. Model performance monitoring tracks metrics such as accuracy, precision, recall, F1 score, and prediction quality. 2. Data monitoring detects missing values, schema changes, outliers, and data drift. 3. Concept drift monitoring identifies changes in relationships between input data and target outputs. 4. Prediction monitoring monitors prediction distribution, confidence scores, and anomalies. 5. Infrastructure monitoring tracks CPU, GPU, memory, storage, and network utilization. 6. Latency and throughput monitoring measures inference response time and request handling capacity. Why ML monitoring is important: detects model degradation, prevents inaccurate predictions, supports automated retraining, improves reliability and scalability, helps maintain compliance and governance. Common ML monitoring metrics: accuracy, drift, feature drift, prediction drift, inference, latency, error rates, resource utilization. Popular tools: Prometheus, Grafana. Evidently AI Labs, Arize AI MLflow. From an MLOps perspective, ML monitoring is a critical production practice that enables observability, automated alerting, retraining decisions, troubleshooting, and continuous improvement of machine learning systems. Nice. Let's continue. Question 2. Explain alerting in ML systems. Here's a strong way to approach it. Alerting in ML systems is the process of automatically detecting and notifying teams about issues, anomalies, or performance degradation in machine learning pipelines, models, or infrastructure. The main purpose of alerting is to ensure production ML systems remain reliable, accurate, and available by enabling rapid detection and response to problems. Common alerting areas in ML systems: 1. Model performance alerts triggered when accuracy, precision, recall, or other metrics drop below thresholds. 2. Data drift alerts detect changes in input data distribution compared to training data. 3. Concept drift alerts detect changes in relationships between features and target outcomes. 4. Inference latency alerts triggered when prediction response time becomes too high. 5. Infrastructure alerts monitor CPU, GPU, memory, storage, and network utilization. 6. Pipeline failure alerts detect failed training jobs, ETL issues, or deployment failures. 7. Prediction anomaly alerts identify unusual prediction patterns or abnormal outputs. Common alerting workflow: 1. Monitoring systems collect metrics and logs. 2. Thresholds or anomaly detection rules are applied. 3. Alerts are triggered when conditions are violated. 4. Notifications are sent through email, Slack, PagerDuty, or incident management systems. Benefits of alerting: faster incident response, reduced downtime, improved model reliability, automated operational monitoring, better SLA and compliance management. Popular tools used: Prometheus, Grafana, PagerDuty, Datadog. Evidently AI Elk Stack. From an MLOps perspective, alerting is essential for proactive monitoring, operational stability, automated remediation, and maintaining production-grade AI systems. Great. Moving on. Question 3. What is data labeling? Here's a strong way to approach it. Data labeling is the process of identifying, tagging, or annotating raw data with meaningful labels so that machine learning models can learn patterns from the data during training. The labeled data acts as ground truth for supervised learning models. Types of data labeling: 1. Image labeling, bounding boxes, segmentation, facial landmarks, object tagging. 2. Text labeling, sentiment analysis, named entity recognition, spam classification. 3. Audio labeling, speech transcription, speaker identification, sound classification. 4. Video labeling, object tracking, activity recognition, frame annotation. Example: email marked as spam or not spam, image tagged as cat or dog. Importance of data labeling: improves model accuracy, enables supervised learning, helps models understand patterns correctly, critical for AI training. Quality common challenges: time-consuming process, expensive for large datasets, human annotation errors, data consistency and quality management, scalability issues, labeling approaches, manual labeling by humans, semi-supervised labeling, active learning, assisted labeling, automated labeling using AI models, popular tools, Label Studio, CVAT, Super Annotate, Amazon SageMaker. Ground truth from an MLOps perspective. Data labeling is a foundational step in building high-quality ML systems because model performance heavily depends on accurate and consistent labeled datasets. Alright, next question. Question 4. Explain weak supervision. Here's a strong way to approach it. Weak supervision is a machine learning approach where models are trained using partially labeled, noisy, or imperfect data instead of fully accurate manually labeled datasets. The goal is to reduce the cost and effort of large-scale data labeling while still building effective ML models. Instead of relying only on human annotated ground truth data, weak supervision generates approximate labels using automated or heuristic methods. Common sources of weak supervision: 1. Heuristic rules, rule-based labeling using domain knowledge. 2. Distant supervision, labels generated from external databases or existing systems. 3. Programmatic labeling, automated labeling functions create approximate labels. 4. Crowdsourced labels, labels collected from multiple non-expert annotators. 5. Pseudo-labeling, predictions from an existing model are used as labels for new data. Example: using keywords like excellent or bad to automatically label sentiment data instead of manually annotating every review. Benefits: reduces manual labeling cost, faster dataset creation, scales to large datasets, useful when labeled data is limited. Challenges: noisy or inaccurate labels, lower label quality, bias in heuristic rules, requires strong validation and monitoring. Common use cases: NLP, medical AI, fraud detection, recommendation systems, large-scale enterprise AI systems, popular tools and frameworks, Snorkel, TensorFlow, PyTorch. From an MLOps perspective, weak supervision helps accelerate data preparation pipelines and enables scalable ML development when high-quality labeled datasets are expensive or difficult to obtain. Let's keep going. Question 5. What is synthetic data? Here's a strong way to approach it. Synthetic data is artificially generated data that mimics the characteristics, patterns, and statistical properties of real-world data without directly using actual sensitive or original data records. It is created using algorithms, simulations, generative AI models, or rule-based systems to train, test, or validate machine learning models. Why synthetic data is used: protect sensitive or private information, reduce dependency on real datasets, handle limited or imbalanced data, generate rare event scenarios, improve scalability for ML training. Common types of synthetic data: 1. Tabular synthetic data, structured data like customer or transaction records. 2. Image synthetic data, AI-generated images for computer vision training. 3. Text synthetic data, artificially generated text for NLP tasks. 4. Time series synthetic data, simulated sensor, financial, or IoT data streams. Methods for generating synthetic data: rule-based simulations, statistical modeling, generative adversarial networks, GANs, variational autoencoders, Vs, large language models, LLMs. Benefits: improved privacy and compliance, faster dataset generation, better model robustness, easier testing and experimentation, supports edge cases and rare scenarios. Challenges: synthetic data may not perfectly represent real-world behavior, risk of introducing hidden bias, validation complexity, possible reduction in model generalization accuracy. Popular tools and frameworks: Gradle, AI, SDV, mostly AI. Cynthia. From an MLOps perspective, synthetic data is useful for scalable model training, testing, privacy-preserving AI development, and improving data availability in enterprise ML systems. On to the next one. That wraps up this episode. Nice work practicing, and see you in the next one.